So yeah, welcome everybody, and I guess this is the last installment of a fully online seminar, and hopefully it's not going to be anymore. Okay, so I will talk about entropy modulo P and quantum information, and it's maybe a somewhat provocative title, but let's see what it is. Okay, so there are two main things, of course: entropy modulo P and the quantum information, and the question is, are they somehow connected? So what do you think? Yeah, well, yeah, they happen to be connected, and the connection exists. It may be not entirely straightforward, but I have quite a lot of time to try to explain it. Okay, so there will be a couple of points in the middle in this connection that we will stop and take a look at. And so the first point is what's called Witt vectors, and so they are very closely related actually to this entropy modulo P. And then the Witt vectors, actually, they form a ring, and that ring is isomorphic to Galois ring. And Galois ring is something that's used to construct mutually unbiased bases for qubits. And mutually unbiased bases are very important in quantum information. Okay, so maybe there's a lot of sort of things to digest, and it seems like everything is connected. But just hear me out, and I'll try to explain what these things are and how they relate. All right, and actually, before I start, let me just tell briefly a backstory about this project. So basically, some time ago, I think in 2017, I read a blog post by Tim Leinster about this entropy modulo P, and I thought that's a very cool idea, but it has nothing to do with my research. So I just put it down as an interesting curiosity. But okay, that's it. All right, so then sometime later during the pandemic, I don't know exactly when, but Harry's son gave him this game called Double. And this game is based on a finite projective plane of order 7. And then one day, Harry just walked into my office and he said, well, let's just make this game quantum. And then we tried for some time, and we made it quantum. We basically related something called affine plane to this set of vectors that are called mutually unbiased bases. And it was all very nice and elegant, but then there was just one special case that we got stuck with, which is for the qubits. It's sort of, you would think it's the simplest case. And, I was stuck with it for a long time. And then this year I talked to Peter, who is also here. And I asked him, what can I do with this? We were working on something completely different, but I just asked, I'm stuck with this. I don't know what to do. And he said, well, you should try using these Witt vectors. And then we were doing some calculation with these Witt vectors, and Lord and behold, we discovered again this Leinster's entropy. And so we ended up with some function, and I was like, oh, I've seen this function, and then I remember I've seen this in this blog post. And actually, I invited it's Tom Leinster, not him. So I invited him as well to this talk. All right, of course, this was all, it's not just a random sequence of events. This was exactly planned out in my grant proposal. This is exactly how things were supposed to happen. Okay, right, so now let's get into it. So first, let me talk about entropy in a familiar sense. So, just of probability distributions, okay? Okay, so there are many ways to think about entropy. So you can just think of it as a function. So it's just, you have some n numbers, and you just compute minus sum of p log p. So that's nice. But it also has other meanings. So you could think of it, for example, as it has operational meaning. So if you want to compress some random variable that has some distribution p, then so this entropy basically is a rate at which you can compress. It's sort of the size of the compressed random variable. So that's very important in information theory. But it also has combinatorial meaning. So you can look, for example, at multinomial coefficients. And so let's say you have n numbers, this little n numbers that sum to the big N. And sort of the way this scales as you increase big N is proportional to e to the big N times the entropy of this distribution that you obtain by normalizing them. And it's also proportional to the size of the dimension of the representation of the symmetric group. So it has sort of some combinatorial also connection. And also you can think of it in some sense like a logarithm, because you take a product of two things, then the entropy is just a sum of the entropies. All right, so there are many ways to think about it, but there's also an axiomatic way to think about it. And so this was in Leinster's paper. So he was saying, the way we can think about it is as follows. So imagine you have a process that generates some random variable and has two stages. You first have some distribution P with n outcomes, and then for every outcome you have another distribution Q, and they could have different sizes. And so then the composed distribution is I'm going to write it like this, and it's just like a tree where you first flip a coin, has n sides, with distribution P, and then you flip for each outcome, you flip a different coin with some other possible distributions. And so this entropy, it obeys this chain rule. So namely that if you compose these distributions like this and you compute the entropy, it's the same as the entropy of this first coin flip, this distribution P, and then a weighted entropy of all these possible other entropies of all these other distributions. And so this is not just one property that entropy obeys, but in fact you could also take it as a definition of entropy. So it has been known for a long time that actually any function that satisfies this chain rule is proportional to the entropy. All right, and so this is nice because here there's no logarithms, no nothing. It's just basically addition and multiplication. And so this is this allows to generalize it, to generalize this notion of entropy. Okay, so now, so what is entropy modulo P? So so this is going to be a function that both the input and output is discrete. So we will take n numbers modulo P as input, and we will spit out one number modulo P as output. All right, how do we define this? So the first idea that comes to mind is that we need a log, right? So because if we have a log, then we can just plug it into the formula and that's it. So we want to have a log in a finite field. And for the younger generation, this is the log lady from Twin Peaks. If you haven't seen Twin Peaks, Ronald and I highly recommend. Okay, so how do we cook up this log? So basically, we want a function on these numbers modulo P that obeys this property of the logarithm. Okay, so how do we do this? So the first thing that comes to mind is we could just take the discrete log. So this is something that for quantum computing people is familiar because this is something that Shor-Solomon computes, and so we could just try to use that. But the problem is that this discrete log, it has basically values in modulo P minus 1, because the multiplicative group of this finite field has P minus 1 elements, and so basically it's sort of it doesn't give you the values in the right domain. Okay, so and in fact you could try to basically find some homomorphism from this multiplicative group that we have here when we multiply these things to the additive group on the other side. But basically, there is no homomorphism, and this is because just the size of these groups are not compatible. They don't divide each other. So basically, there is no sort of log the way we would like to. So what can we do? Okay, so here's what we can do. So by Fermat's little theorem, so we have the following equation. So if we take any number, any integer, and we raise it to power P minus 1 and subtract 1, then this result should be a multiple of P. Okay, and you can define something called Fermat quotient, which is basically, so if this is a multiple of P, then you can just divide it by P. So then this is going to be some integer, and then to have it the right values modulo P, then we just take this integer modulo P on top of it. Okay, so now what you can show as a simple exercise using Fermat's little theorem, that this Fermat quotient is a homomorphism. So it obeys this kind of multiplicative mapping multiplication to addition property. Okay, and it has also it takes the values modulo P, so that's also nice. But there's a little bit of a trouble of the input, so I'm not going to go into details, but basically you can also show that
is the Q in the left of the equality, should that actually be P? QQ, you have QQ, that should be P, no? QP A of A times B equals QQ of A plus QP of B.
Oh, yeah.
Just to be sure.
This should be P.
It's a typo. Okay, good.
Yeah, this should all be P. Right. Yeah, so there is a little kind of a glitch with this Fermat quotient, namely that, so the input actually, you should think of it as being modulo P squared, not modulo P. But other than that, it actually you can show that this Fermat quotient is basically the best you can do for logarithm, and any sort of homomorphism that serves the role of logarithm is just a multiple of this QP. Okay, so it's sort of it's a natural notion. Okay, so now so now we have the log, so we could just plug it into the formula. And actually, there's a slightly different way to also think about it. And actually, let me explain also another way to how you can use this this idea to make entropy modulo P. So another way is to, instead of looking just at the logarithm, you can actually look at the minus x log x. Okay, and so this function is called nonlinear derivation. So I'm just going to denote it by this partial kind of derivative. But it's simply because it satisfies the property that if you compute this function for product of two things, then it looks like this. Okay, so it's just like a derivative. And also, if you compute of one, then it's zero. That's also what derivative has. Okay, and so now, with this, using this this partial this nonlinear derivation, you can write the normal entropy. You can write it as you can think of it as that. Actually, the entropy measures the nonlinearity of this function, because so the first term here, that's just a normal term that defines entropy. So this is minus p log p, and the second term here, it's actually zero, because if this is a probability distribution, then this is one, and then this delta one is zero. Wow, it's really lots of sun. All right, so so. And basically, sort of, we throw this thing in here in some sense. Well, if you want to extend entropy to real numbers, not just probability distribution, so there are sort of several possible ways to do this. And here, when we throw in this particular term, which is sort of normally zero, it is not zero when you plug in some arbitrary numbers here. So it's sort of, it chooses one particular way to extend the entropy. But anyway, so this is how you can think of the normal entropy. And so, and then since this Fermat quotient was playing the role of logarithm, then minus a log and this Fermat quotient is basically like the modulo P version of this derivation. Okay, and this approach is a little bit nicer, because here you don't need to worry about sort of like in the Fermat quotient. There's also a slight problem that you have to make sure the argument is not a multiple of P and so on. But basically here, for any integer a, by Fermat's little theorem, a to the p minus a is a multiple of p. So this is well defined for any integer, and you can just compute it. And then by analogy with this normal entropy, we can define this entropy modulo p just using the same equation. Okay. All right. So so now let's look at how it if we write it out, how does it look like? And so so if you plug in this this p derivation is just a polynomial, basically a minus a to the p. And if you plug in it and simplify it, what you get is this. So basically, you can think of this entropy modulo p as sort of, well, you can think of it, it measures the sort of the nonlinearity of raising to the power p. If raising to the power p was sort of fully linear, then this would be zero. Okay, but so here in this formula, for this formula to make sense, so you could actually plug in any integers here on this side. And it's a bit suspicious if you want to plug in integers modulo p, because here you need to divide by p. So it seems like, well, can you actually, so this is like a, we're almost there, but the input now is not modulo p. And what you can do is you can basically show that actually here you can just expand it essentially. So if you expand it and use multinomial theorem, then so the terms where x is raised to the p will cancel out because you subtract them here. But then all the other terms, they will have some coefficient that can be divided by p. So you can make sense of this division by p without any sort of any dividing by zero or anything like that. And so basically using this fact that if two integers are the same modulo p, then their powers are the same, then their p's powers are the same modulo p square, you can show that actually this entropy, that you can treat these inputs here as modulo p. And then if you expand it, you can get like a polynomial function, a polynomial expression for it where there's no division by p. And so here there is still some kind of division by these factorials, but these factorials, they don't really cause any trouble because these numbers they are less than p. So because we kind of subtracted this largest term that has power p. So, and these you can think of as just, if you work in a finite field, you can just invert these numbers, basically modulo p, and that's, you could, instead of dividing by them, you can just multiply by their inverses, okay? And so this is just a polynomial essentially over the finite field, and we can take this as the definition of the entropy. All right, and okay, this all might seem kind of maybe contrived. Yeah, okay, we're just kind of cooking this up. Why is it, does it mean anything? Or maybe there are other ways to cook it up. And so what Leinster shows in his paper is actually that any function that on integers modulo p that satisfy the chain rule, it has to be proportional to this function. Okay, so basically it says that this actually is sort of the unique definition of entropy modulo p. Using this chain rule as an axiom, just like this was also the axiom basically for normal entropy. All right, so now we have this entropy mod p. So now the question is, what can we do with it, and how does it connect to quantum information? Okay, so now the way it connects is through these mutually unbiased bases. And so the mutually unbiased basis is basically some nice set of vectors in the Hilbert space, and they sort of they form some kind of some order in the otherwise big and chaotic space. Okay, so let me just define them. So we have a bunch of vectors, and they are in a complex space of dimension d. And I will use two indices for these vectors. And so the index A will have d+1 values, and the index B will have d values. And these vectors have very specific inner products. And so what these inner products, so the way you can think about it is that this label A is like a basis. It labels the basis, and B labels a vector within the basis. Okay, and so what this equation is saying, that if you take two vectors from the same basis, then they must be orthogonal. So that's what it's saying, that this is a basis basically if you fix A. Okay, what else is saying is that so there are d+1 of these bases, so d+1 values of this parameter A. So it says that there are these vectors, you can partition them into d+1 orthonormal bases. And then, the second line is basically saying that if you take two vectors from different bases, then the inner product, absolute value square, is always going to be 1 over d. It's always sort of the same. Okay, so it doesn't matter which. Oh, there's somebody asking a question. Is a way in which letting p go to infinity gives the usual entropy? Oh yeah, so that's a good point. So yeah, no, I don't think so. But in Leinster's paper, he also talks about this entropy p being a residue of the normal entropy, and maybe if you look there, maybe that helps you answer the question. Okay, so now if we need to cook up these mutual unbiased bases, what we can do, we can always just rotate these vectors, and we can just take one of these bases to be the standard basis. So that makes things easier. And if we do this, actually what happens is that because of this equation, if we take any vector from any of the other bases and one of the standard base vector and compare them, what this equation is saying that the the inner product square should be 1 over d. So it means that all these other vectors, they should have amplitudes, all the amplitudes should be 1 over square root of d. And so basically, if you want to find these mutually unbiased bases, all you need to do is just to find the phases. So basically, for every entry, for every coordinate, you need to find some kind of e to the I phi that achieves these right inner products. Okay, so now, the canonical example, the simplest case is d equals 2, and these are just the states that we are familiar in quantum information. So basically, so this is the Bloch sphere representation. So here all the angles are increased by a factor of 2, but basically 0 and 1 are normally orthogonal, plus and minus are normally orthogonal, and these are also plus I and minus I normally orthogonal. And then here, they have 180 degrees, and then if you take any two vectors that are not in the same basis, then they have 90 degrees. And if you divide this by 2, then you get 45, and then you get sort of the right inner product. Okay. So this is the sort of the simplest example. Wait, let me just close my window. There's too much sun.
Marius, there was a question in the chat.
Oh, yeah.
The question is there a way of in which letting p go to infinity gives the usual notion of entropy?
P equal to 1. Yeah, so there are some papers about P going to 1, but I'm not sure what you get in that case, actually. Yeah, there are some papers that
Yeah, I was just guessing because you have these things like x to the epsilon minus 1 divided by epsilon goes to log x if epsilon goes to 0. Maybe it sounds vaguely similar, but I haven't checked.
Yeah, but there are people. There is actually Cons and somebody else. They work. They have some kind of ideas about the Riemann hypothesis, and they have some paper about this sort of yeah, where you kind of have P equals 1. But I don't really understand or know anything about it. Okay. All right. So now, how do you make these mutually unbiased bases? So we want to make these vectors. And so here's a construction. So let me take the dimension to be a power of a prime, and let's take P to be odd. And so let omega P be just a P roots of unity. And so then you can make this vector as follows. So as I said, all the amplitudes should just have absolute value 1 over, so here dimension is, so here the dimension is just P. So all the amplitudes are just 1 over square root of P. And so then we have some superposition of the basis states that I will just label by elements of the finite field, just numbers modulo P. And so the funny phase that you need to choose has this kind of quadratic polynomial in the expression. And then you can, it's sort of not too hard to check that they have the right inner products. Okay, so then if you want to generalize this from a prime dimension to prime power dimension, then all you need to do is, well, you need to change the normalization, you need to change the sum to the bigger field. And now if you work in the extension field, fp to the n, then this expression is not anymore a number modulo P, so you need to apply this trace map. So this is sort of like a canonical way you can get from this extension field to the base field. And now you have numbers modulo P, so you can raise your omega to the power of P. And basically using similar calculation, you can also check that this construction works. Okay, so now, so what we did with Harry last year is when he asked about this double game. So we related this mutually unbiased basis to an affine plane. So let me explain how this works. So an affine plane is just a configuration of a bunch of points and a bunch of lines. So let's say we take the size of this plane to be, well, or I don't know what is it called, the order of the plane to be 3. So then we just take a 3 by 3 grid of points. And through these points, we take all possible lines at all possible slopes. So you just think, let's say, so these are the horizontal lines, then you have vertical lines, then you have the lines of slope 1, and then you have the lines of slope -1. And so, these curvy things, it's just, I just kind of make it wrap around. But because we work modulo 3, these lines kind of wrap around like this. Okay, so this is affine plane. You can generalize it in the obvious way. And so we can now, what we can do is we can sort of make quantum states that represent the lines in this plane. And I will call these the line states. Okay, so what's the construction of these states is, so there's a special case when the lines are vertical. So so the A will be the slope of the line and B will be sort of, the height or where it starts. And so if A is infinity, so these are vertical lines, so they just look like this. So they are all the points where you fix the sort of the x coordinate, the first coordinate, and then the second coordinate varies. And then the other lines are just, you have x in the first coordinate, so you choose some x coordinate here, and then you just compute what is a x plus b, and that's your line. Okay, so these are these are vectors in dimension q square, and they sort of encode the structure of this plane sort of in a very natural way. Okay, and now these line states, the reason they're interesting because the inner products between them, or the Gram matrix, looks very similar to this mud matrix. So basically, if you take two line states that have the same slope, then these lines are parallel. So if I take, let's say, these two lines, these horizontal lines, then these points are completely disjoint, and so they will have inner product 0. And of course, if I take the two lines to be the same, then the inner product will be 1. Okay. And then this second case, this just means that any two lines that are not parallel, they have exactly one point in common. So, you know, I don't know, let's say if I take a horizontal line like this and a line that's at slope -1, then they have 1 point in common, okay? And so it's easy to see that these line states have these inner products. This just kind of reflects the combinatorial structure basically in this affine plane. Okay, so now, you know, the observation that we made with Harry is that these line states, they are basically somehow similar to a pair of these mutually unbiased basis vectors. So basically the Gram matrix of these line states is exactly the same as the Gram matrix of these MUB vectors, but you know, you need to square these MUB vectors, and so therefore you need to kind of take 2 copies, and then, you know, to get the right, to get this absolute value square, you put the complex conjugate here, okay? All right, so now, so that means that since I have the same Gram matrix, then, so these are both in dimension like Q square, where Q is the size of the finite field. So then there must be a unitary transformation that maps one to the other. And, you know, it's not obvious what the transformation should be, but we figured this out. And basically what you need to do is you just need to apply Fourier transform on the second register, and then you apply some permutation matrix. So the Fourier transform is just the standard Fourier transform, except if we work over an extension field, then you again need to take a trace here, but otherwise it's just what we're used to in quantum computing. And this P operation, it's a permutation matrix. It preserves the basis, you know, it maps basis states to basis states. There are no funny sort of, you know, complex numbers or anything. And it just maps X and Y to basically the X plus Y divided by 2 and X minus Y divided by 2. And so it's a, you know, once you know that this is the answer, that this is the unitary, it's a simple exercise to check that this works. And, you know, if you want to draw it as a quantum circuit, then this is the line state, and you apply your F, and then you apply P, and then you get these guys. And, you know, I'm trying to revolutionize the field, so I'm drawing the circuits in the other way around. So the time goes from right to left, which is the way they should be drawn. Okay, so, right. Now, so this is all very nice. This works for any finite field, except it doesn't work in characteristic 2, because here we need to divide by 2, and this is just not possible. Okay, and so basically, so we had this really elegant relationship between affine planes and mutually unbiased bases, but there's just one special case in which it doesn't work. And I thought, yeah, this is going to be easy to solve. You know, we leave it for later, do some other things, and then we solve it afterwards. But actually, it's much more complicated than the general case. And it, you know, the rest of the talk is, you know, what do you need to do? So in the general case, you just use this equation, and this is really a simple calculation. You could give it as an exercise to an undergraduate student, but the general case really involves a lot of new and interesting mathematics. Okay, so now, so let me just for comparison show you how the formula looks like in the even case of these mutually unbiased basis vectors, so we kind of know where we're getting to. So this was the normal formula. And so in dimension 2 to the n, you need to use a formula that looks, you know, maybe somewhat similar. So now what are all these things here? So basically here, so we were performing all these calculations in a finite field, but here we are doing this in a Galois ring, and I will sort of briefly talk about what this is. Now, so what is this? So now here the sum was over all the elements in a finite field, but here it's over some set Tn. And so this Tn is called the Teichmuller set. It's some kind of subset of the Galois ring. And it has a special property that if you sort of take it modulo 2, in this case, because we're working sort of, you know, modulo 2, then it gives you back the finite field. So in some sense, this set is somehow similar to the finite field, but it, you know, you can see it only when you take it modulo 2. Otherwise, it has sort of, it's closed under multiplication, but it's not closed under addition. It sort of has a little bit of unpleasant structure. Okay, and so then this trace is somehow analogous to the trace in a finite field, and it just maps your Galois ring element to a number modulo 4, and then you can raise your I to that power, and then you get your states, basically. And by the way, also you can see here, what's interesting is that you would expect normally to be -1 to the power, you know, something. Just like here, you have the sort of the prime basically is P, and here the prime is 2. But you don't get 2, you get I somehow. Okay, and so this is also only this standard example that I showed earlier, this in the block sphere. So these plus minus I states also, you can see that you basically need an I, otherwise you will kind of stay in this circle. You cannot really get all these orthogonal vectors here. Okay, right. So now let's talk about what all these things are. So we need to understand the Galois fields and the Galois rings. Okay. All right. So so let's first talk about these extension fields, just for finite fields, and how it compares with the Galois rings. So basically, if you have a finite field, just numbers modulo p, you want to extend it to degree n. You can think of this fp to the n as polynomials, basically, and you have to kind of compute modulo some monic irreducible polynomial f. Okay, so you would write it like this. So this basically means that if so this f has degree n, and so if you multiply polynomials and you get something that has a degree bigger than n, you can always basically use the equation f of z equals 0 and just kind of knock the degree down. So basically this just means that you multiply polynomials and you always knock the degree down below n using the equation f equals 0. And the addition is sort of the same way as you would expect normally. The coefficients are modulo p. Okay, so now the Galois ring is basically the same idea, except instead of starting with a finite field, we start, numbers modulo p, we start with a ring. So we start with numbers modulo p to some p to the k. Okay, and so there's some, whatever, again, basic primitive polynomial, which is a certain polynomial with certain properties. And if you, again, do arithmetic in this kind of base ring, and you knock down your degree of polynomials to degree below n, then that's how you get your Galois ring. And so I think it's also nice to kind of see how this Galois ring is sort of a generalization of the finite field. So basically we have these two parameters. So we have the k parameter that says what the base ring is, and then we have the n parameter that says what the degree of extension is. And so if we put it on the two axes, then when both parameters are 1, then this Galois ring just becomes fp. So there's just polynomials basically of degree 1 I guess less than 1. So you just get fp. Now if you take k equals 1 and then you just extend, you will just get the normal finite field. Now if you instead increase k, then you get basically integers modulo some prime power like p to the k. And if you take these parameters both big, then you get this general Galois ring. But basically, everything in this table is a special case of the Galois ring. Okay, so there is, in some sense, there's the extension field sitting inside it, and there's also the base field also sitting inside it in some sense. Okay, so so let's look at some examples. So basically, if we have a field of 4 elements, we can think of it as polynomials modulo some. This will be a specific choice of this irreducible polynomial. And so this just means that if we take this to be 0, it means modulo 2 that z squared is equal to z plus 1. And so, this just means we have all polynomials that are degree 1, like they're constant or linear. And if we multiply them, we get z squared, and we just knock it down to z plus 1. Okay. And so similarly, so if we have, for example, a Galois ring, so we can start instead of with numbers modulo 2, we start with modulo 4. And so then let's say, take a degree 2 extension. It looks similar, and in fact, the polynomial looks the same. So we have now polynomials modulo 4 with coefficients modulo 4, and we use this, to decrease the degree. And so the elements of the Galois ring in this case are just all constant and linear polynomials with coefficients modulo 4. And they are subject to, so here if we set this to 0, then we get minus z minus 1, which is the same as 3z plus 3. So we use this equation to decrease the degree always below 2. Okay, so now, and what you can also see that within this Galois ring, there is actually a finite field sitting. So if you take these guys, and instead of working modulo 4, if you work modulo 2, you can see that this identity reduces to the z squared plus equals to z plus 1. So it's the same identity as here. And also these elements, you would basically clump them together like in pairs. So you would map, like if you work modulo 2, you would map 0 and 2 together, and you clump 1 and 3 together. And so basically, you would end up getting the same elements as here. I guess you would clump 4 of them together. So there are 16 elements here, and there are only 4 elements here. But you will basically just recover this field F4. Okay, so that's the sense in which there is a field sitting within this Galois ring always. And more generally, if you have this general Galois ring and you work modulo p, then this becomes the field of degree, the field modulo p of degree n. Okay, so now let's discuss next. We need this Teichmuller set. So remember that in this expression for the mobs, there was some funny set t. And so it's just defined as 0, 1 and all powers of z until it kind of wraps around. And so this the size of the set is p to the n, and as I said, so it has the property that if you take modulo p, you get this field. So basically, this is a set that is, you can see it's closed under multiplication, but it's not closed under addition. But if you take modulo p, then you just recover the finite field f p to the n sitting inside there. Okay. And then basically the inverse, so that the reverse of taking modulo p is called Teichmuller lift. So basically any element in this set that if you take modulo p, you get some finite field element, and so the reverse map is called Teichmuller lift. So let me just give you an example. So again, if we have this, for example, this Galois field of modulo 4 of polynomials of degree 2, then the elements of the field are just these polynomials. And so now if you take the modulo 2, you get this field F4 that I showed earlier. And the Teichmuller lift is just, it's the reverse map. So it maps, everything to the same, and then it maps the z plus 1 to the 3z plus 3. And so here, this is closed under multiplication and addition, modulo the right polynomial. But now this is kind of a bit nasty set. It's closed only under multiplication. So it's sort of, you choose some representatives basically for when you lift these guys, you kind of lift, you have to choose which way you're going to lift. All right. So that's how the field sits inside this Galois ring. Now we need also the trace. So that's a map that takes basically these polynomials and maps them back to numbers. So the way you can think about it is as follows. So if you work in a finite field, so this extension field p to the n, you can think of it as a n-dimensional linear space over the base field. And so the basis for this space are just these monomials. So the z is always the variable in which the polynomials are. And so they are basically, if your degree of the polynomial is less than n, so then this is, you can think of this as a basis. And so, any polynomial is just a linear combination of these. But then also multiplication by elements of the field, you can actually represent them by a matrix, so we'll call it the capital X matrix, that acts on this basis somehow. So it's an n by n matrix of over the base field. So that's, you can think of the extension field as polynomials of degree at most n, or you can also think of as a special set of n by n matrices over the base field. And it's not all matrices, but it's really a very special set. Okay, and so then the trace, you could say, well, it's just you represent your element by a finite field element by this matrix and by n matrix, and you just take a trace of that. And that's one way to think about it, but there's also kind of algebraic expression which looks like this. And so it's, it's not clear why these two things are the same, but they are. And also the trace is linear, so it's clear from this matrix kind of definition, but from this algebraic definition, it's not clear at all. And that's one of the important properties of the trace, that it's linear. Okay, and so in a Galois ring, it's very similar. So we use basically the same algebraic expression as here. And so this sigma to the I, it means we apply I times something called a Frobenius map. So this sigma, and in a finite field, this Frobenius map is just raising to the power of p. And in this Galois ring is more complicated. I'm not going to go into details, but basically this formula is kind of analogous to this formula if you think of the sigma as kind of just raising to the power of p in some sense. All right, so this defines the trace. And so now let me just show you quickly again this example. So this was the formula that we have for these mutually unbiased bases for qubits in dimension 2 to the n. And so let's say we look at this example of 2 qubits. So we have n equals 2, then we use this Galois ring that I showed before. And so this Teichmuller set is 0, 1, and then all the powers of z, which simplifies this. And then you can compute that the trace of this element z, this kind of the variable that I use in polynomials is 3. If you represent it by a matrix, then you just get 3. And using that basically by linearity, you can compute trace of any element of your Galois ring. and then you can sort of plug all this in and you can get these expressions. So basically, so the columns of these matrices are the vectors in your mutually unbiased bases in dimension 4. And so this A equals infinity, so these vertical lines, so these are the standard bases, and all these other ones, you can see they have absolute value 1/2. All right, so you can see this is kind of somewhat complicated. And basically, the problem is that if we want to also relate these mutually unbiased bases in the qubit case to these affine these line states, to basically the affine plane over the field F to the n, we immediately run into the problem that here this is the bases are labeled by the elements of this Teichmuller set, but in the line states it's just labeled by the elements of the finite field. And so we kind of have some kind of mismatch. And so basically, I really struggled with this formula for a long time. And I just, all I want is just to convert this formula into the finite field, just have a sum of the finite field and no funny Galois stuff. I just want to have just basically no rings. I just want to have a field, okay? And so this is the remaining part of the talk. I will explain how you can massage this formula to just get rid of all this Galois ring stuff and just express it only purely in terms of the finite field. All right. So now this is where these Witt vectors come into play. So I was stuck with this for a long time, and then I asked Peter, can you help me? And he said, well, you should take a look at these Witt vectors. So now I'm gonna again switch completely the gears and talk about something completely different. Okay, so let's say you have some ring R. It could be any commutative ring. And we will take pairs of elements from this ring, and we're just going to call this set of length 2 Witt vectors. Okay, so just a pair of elements in the ring. Now, so now let's come up with. So there will be some functions that map these vectors to just one element. So basically, there are 2 components. We just want to map to a single element from the ring. And so these are called the ghost components, and so they will depend on some number p, and sort of. The way you can think about it is that this is a number that has 2 digits and you write it in base p. And so then the last digit of this number is x0. And then the last 2 digits, if you kind of, put them together in a number that's in base p, then it looks like this, except there is this annoying thing that I don't understand what's the intuition. You have to raise this x0 to the p. So if you didn't have this x0 to the p, if you add just x0, then this would be just a natural sort of the, if this is a modulo p number, then this would be its value, basically like modulo p squared. But basically, this raising to the power p makes things more interesting. But so this is just a definition. These ghost components are just defined like this. And now what we're going to do is we can just turn these Witt vectors into a ring. So we can define addition and multiplication, and they are defined by demanding that these ghost components are homomorphisms. Namely, that if we add 2 Witt vectors, so the xy are a pair of elements in the ring, if we add them and then we compute this ghost component, any of these 2, then it has to be compatible with addition, and it has to also be compatible with multiplication. And so these equations, so here this is the undefined operation, and this is the addition of these Witt vectors, and these equations implicitly define this operation. And so similarly here, this is the multiplication of the Witt vector that is defined implicitly like this. And so this is here on the other side, these are, the output of these ghost components are just elements in the ring. So, all right, so this is how you set things up. And so this is very general. This ring is completely arbitrary commutative ring. Now, if you work it out from these definitions, what you get is the following. So basically, the addition and multiplication in this Witt ring looks as follows. So if you add 2 vectors, it's the same as just adding them basically component-wise. But then from the second component, you have to subtract something, and it turns out what you have to subtract is exactly this modulo p entropy of the first components. So here, remember again this. Modulo p entropy was just a polynomial. So if you have 2 variables, you can just write it like this. And if you don't like dividing by p, you can just expand it, and then you can cancel out the highest order terms with a power of p, and then all the remaining coefficients, these binomial coefficients, you can just divide them by p. Okay, and so this works in any ring. And similarly, the multiplication, you just get this formula. You could also take this as the definition of this Witt ring. So you can say these are just, pairs of elements from the ring that have these funny rules for addition and multiplication. And then you can check the 0 element is just this and the 1 element is just this. And okay, so then what's interesting is now you can check that the addition of these vectors is associative. And actually, this associativity of this addition is equivalent to this kind of co-cycle condition for this entropy mod P. And so this equation actually is also in Leinster's paper, and this was in some earlier papers where people were kind of coming up with this entropy mod P ideas. And this is just basically saying that these Witt vectors, the addition is associative, this co-cycle condition. And similarly, the multiplication being distributive gives another equation for this modulo P entropy. But basically, what I'm saying is that these Witt vectors, I think, is a really nice source of all kinds of identities and properties of this modulo P entropy, because their properties literally translate, their arithmetic literally translates into properties of this entropy. And this is over any ring; it doesn't have to be modulo P. All right. Now, so the relation. So how does this, relate to what I talked about previously? So these Witt vectors are basically isomorphic to the Galois ring. So I think maybe I should not go into too much detail, but okay. So so what you can do is, if you have your Witt vector, you can just map it to this Galois ring by basically lifting these two field elements into the ring, and then you have to. So this 1 over P here, I didn't know you have to do this. I was really struggling with this for a long time, but I found this. Basically, there are many papers that say that these Witt vectors are isomorphic to Galois rings, but there's only one paper which says what the isomorphism is. And so anyway, so basically this is the isomorphism. So if you have the Witt vector, you just kind of lift it you lift these finite field elements to the ring, and you do this. And similarly, if you want to go the other way, you do this. Okay, and so this basically lets you translate all this Galois ring stuff to just pairs of elements over the finite field. All right. Now, okay. So now the final thing we need to translate is to take the trace of the element of this Galois ring, and that we can also do in terms of Witt vectors. And so first we need to define this Frobenius map, which is basically raising to the power of P. So you just component-wise literally do that, and you can check that this is a ring homomorphism. And and then again, from checking this, you get some nice identities. For example, this modulo P entropy, it commutes with this raising to the power of P. So you can first raise your elements to the power of P and compute the entropy, or you can do the other way around. So that's another nice identity you get from these guys. Okay, so now, and then you can define the trace of a Witt vector, and it's just defined using the same kind of idea that you take this Frobenius map, apply it k times, and then you sum everything together. But here the sum has to be computed in this funny sense. So remember, these Witt vectors, they have this funny addition where when you add them, you kind of add component-wise, but then in the second component, you subtract the entropy from the first components. And so then what happens is, with this formula, you can actually get a really nice formula for how to compute the trace. So if you have an arbitrary Witt vector, the trace of this Witt vector is just a trace component-wise, and then in the second component you subtract some funny function, kind of like entropy of the first component. And so I think this funny function is very interesting. So I don't know what this function means, so I'll just call it the mystery entropy function. But so this is a function from the extension field to the base field, and it's just equal to the entropy of this distribution, where you basically. So you take a single element of your field, and you raise it all possible powers, p to the power k. So this is also called Galois orbit, and then you compute the entropy of that. And you can also rewrite it like this. So you can, in some sense, it measures sort of how much the trace doesn't commute with raising to the power of p. But so this function somehow is very important, but I don't really know what it means. And so you can check, for example, that this trace of these Witt vectors is linear, as it should be. And for that, you get some interesting identities for this entropy modulo P. And so what this identity, for example, is saying that, and so this is actually funny. So like, in quantum computing, if you want to compute the entropy of a state, what you do is you first take a trace, and then you get a mixed state, and then you compute the entropy. And so, in these, when you deal with these Galois rings or these Witt vectors, you can also first compute the trace, and then you compute the entropy. But you can actually do the other way around. You can first compute the entropy in the extension field, and then you take a trace, and then you go to the base field. And so basically, how much the trace doesn't commute with this entropy is exactly also how much this funny H function is not linear. So you can get, for example, this kind of identities. And I don't really know what this little H function means, but it seems that it kind of comes up a lot in this stuff. All right, so now we have this trace of the Witt vector. So now let's just go back to the MUBs. Let's put everything together. All right, so now, so what we had, so the thing I was struggling with is that in the MUBs, in the exponent, we have I to the trace of this Galois trace. And so all this Galois stuff that I don't like. So let's just translate it to these Witt rings. So basically, using this isomorphism between these Galois rings and Witt rings, we can just replace a plus 2b by ab square, and then this x becomes x0. Now we can multiply. So there's the rule for the funny rule for multiplication of these Witt vectors. We get this. And there's a formula for taking trace, which is just component-wise taking trace and subtracting this mystery function or computed on the first component. So we can do that. And then we can just use the isomorphism the other way around and go backwards, and then we get an expression. And so basically, so this here is a number modulo 4. So this is like a 0 or 1, and this is also 0 or 1, and then this is plus 2. And so this lets you basically compute this trace purely in terms of finite field elements, and there are no Galois stuff anymore. All right, so now what we can do, we can take this mutually unbiased basis expression that involves all these Galois rings, and we can just rewrite it completely only in terms of the finite field. And so what we have is that we have to raise I to the trace of AX. So the A and X, now everything is in a finite field. And then we kind of separate, this is the power of I, and this is the power of -1. So basically the power of I is completely determined by this, and this is either 0 or 1. And then there is some expression here for the power of -1. And you can see this mystery entropy function creeps in here. Okay, but so, basically this is a this expression is completely just in terms of the finite field. And, you can compare it how it looks like in the general case. And I would like to understand, is there any way to sort of write this formula so that it looks the same for any prime? So here now there's kind of a discrepancy. So like we're summing over all the finite field, and there's some normalization as you would expect, but then this phase here is completely different from what you have here. All right, so and now what we can also do, we can have an explicit circuit that maps these line states over the affine plane of size 2 to the n to the mutually unbiased basis, because now we don't have any Galois stuff, and now we have the finite field here and we have the finite field there, and we can do this. And so this was actually really a long struggle to get this. But basically what the circuit is saying is that, you apply Fourier transform. Then if this register is not 0, you apply Fourier transform. Then you apply a diagonal matrix that computes this mystery entropy in a phase. Then you apply a matrix that squares your element in a finite field. Then you apply Fourier transform again. Now this is, if this is not 0, you multiply the first register with the second. Then you add the first register to the second, and then you do inverse of the square root of the swap. But so basically every gate in this circuit is sort of, some kind of obvious unitary or some operation in a finite field, like, this is a diagonal matrix, or this is like squaring, and everything is invertible. Everything is clearly unitary. So this like squaring is invertible modulo 2 in a finite field as well. And so basically this sort of, it's obvious from these expressions that this is a unitary, and then this is a long calculation to check that it actually works. But it turns out that it works. All right, so yeah, so now let me just summarize. So this talk was about entropy modulo P and quantum information, and the connection through, this connection is not so obvious and goes through all these other points. So first, the first observation was that these Witt vectors, they can be defined over any ring, and their addition just happens kind of component-wise. But then in the second component, you have to subtract the entropy of the first components. And so this kind of, in this Witt vector world, this entropy mod P kind of crops up very naturally. And if you take a trace of a Witt vector, then also you get this mystery function here, this H in the second component. Okay, so this is how the Witt vectors connect to the entropy. Now these Witt vectors are just isomorphic to the Galois ring. So we are interested in this ring modulo 4 of degree n. So this is just a pair of elements in a field of size 2 to the n. And we can evaluate this funny this Galois ring thing that I was struggling with for a long time. We can just completely write it in terms of the finite field. And again, there is this interesting mystery entropy function appearing here. And now we can plug this into the formula, and we get an expression for mutually unbiased bases, just purely in terms of the finite field. And also this mystery entropy function creeps in here. So this is how the connection works. So I hope that now it makes sense and that you are all now converted to believers that this is, it's not just a conspiracy theory, it actually is all connected and makes sense. All right, so here are some open problems. So I'm still kind of unsatisfied that these expressions look so different in a case when the prime is even and when it's not. So it would be nice to have some kind of a single expression where you could just plug in either, either 2 or some odd prime, and it would always give you the right mutually unbiased base vectors. And also these circuits, they look very different in the two cases. So it would be nice if you could somehow have a sort of a single unified circuit, and it just somehow simplifies in the case when the P is not even. So then the other tantalizing question is, what does this function HP mean? So this is like the entropy of basically the Galois orbit of this field element. And it seems like it should have some kind of meaning also in information theory. Maybe there's some kind of analog of it in the continuous world, but I don't really know. And in fact, the related question is, I think, what would be a quantum entropy modulo P? So is there, can you take n by n matrices of the finite field and define some kind of entropy of that axiomatically using, let's say, the chain rule? And what would that be? And in some sense, also this mystery function is kind of a little bit like that, but I don't think it really is. Well, anyway, so because it goes from the extension field to the base field, so it maps basically matrices of the finite field to the elements of the finite field. So it's kind of like, that would be kind of like a von Neumann entropy on quantum states, but yeah, I don't really. But the field is commutative, so it's sort of, I think maybe, yeah, I don't know. Maybe if it is extended to all matrices, just from these special matrices that represent the finite field, if you extend them to all matrices, maybe then you get some notion of a quantum entropy might be. So I think in general, also one conclusion is that these Witt vectors is really a great source of identities and properties of this entropy modulo P. And actually these Witt vectors, they don't have to be length 2. In fact, normally they are actually infinitely not long. They have infinitely many components. And they are important, for example, the p-adic integers are constructed by taking these infinitely long Witt vectors. And so, you could just take them of length 3 and look at what's the formula for addition. There should be all kinds of crazy entropies creeping up there. So it'll be interesting to know, if there is some more interesting entropies or polynomials basically can be obtained from these guys. Then I think also for any, information theory person, an obvious question is, what is the meaning, what is the operational meaning of this entropy modulo P? So just like the normal entropy, it is kind of the rate of compression. And is there any sense in which this entropy mod P also represents a rate of some kind of process? And you could also similarly ask, does it have a combinatorial interpretation? Does it count some, some things, or is it like the asymptotic rate of growth of some combinatorial objects? So that I don't know. And of course, one can build a whole information theory modulo P. So you can ask, are there other entropies? Is there, like, for example, mutual entropy? Is there conditional entropy? Is there a relative entropy modulo P? And I think it should not be too complicated just by analogy to cook these things up. But it would be interesting to know, do they exist? Are they unique? And sort of, do they have similar properties and so on? Okay, so then more about these affine planes. I think an interesting question is as follows. So basically, I talked only about these kind of like standard affine planes that are obtained from finite fields. And so they have some property that's called the Desarguesian property. But however, there are other affine planes that don't have this property. For example, in dimension 9. So there's a nice book by Bruin and Kirkpatrick that discuss specifically this case. And so basically these kind of exotic affine planes, they are not isomorphic to the normal ones, so they're really different. But however, if you write them as quantum states, if you write them as these line states, then the Gram matrices of these sets of line states are the same, because these, it's just about inner products or about how many points they have in common. So if you have, a bunch of parallel lines, they have no points in common. If you have two non-parallel lines, they have exactly 1 point in common. And so basically the Gram matrix of a non-Desarguesian affine plane is the same as a Gram matrix of a Desarguesian one. And so there must be a unitary that converts one into the other. And so they must be isomorphic in some quantum sense, even though they are not isomorphic in classical sense. And I think it'd be interesting to know, what this isomorphism is, like just to have an explicit unitary, basically. And then once you have it, then you can also establish a connection with the mutually unbiased bases. All right. And, of course, I think also it's really interesting to ask, what is the meaning of this entropy modulo P? Does it have any sort of meaning in physics? And I think, if there's anything we should have learned from quantum information is that we shouldn't trust computer scientists. Even though they came up with a really good definition and notion of computation and information, then it was not the most general one. So there's a deeper notion, and that was really what physicists suggested, that we should use quantum mechanics. And of course, physics is not finished. There's still the problem of unifying the gravity and quantum mechanics. And so, it could be that there's an even deeper notion of information and computation. And I think it's good to just keep our eyes and ears and minds open to sort of interesting other notions of information, basically, that could appear, and see maybe they could be used for something. And that's the tantalizing question: does it really have some meaning in physics, or is it just a red herring, or a green bugger? So that's it for my talk.
Thank you, Marius. Let's unmute and give Marius a hand. Other questions? Someone raised their hand. Peter?
Yes. Thanks a lot for a very interesting talk. One question which came up was about combinatorial and information theoretical mailing, but you raised that yourself already. So given the fact that you raise it as a question, I understand you don't have an answer. The second point is that I may have a suggestion. I'm not sure whether it leads to anything, but I remember from a long time ago when I was at CWI, at the Mathematisch Centrum, I had a colleague there who worked on transcendence functions in characteristic P. And what she basically did was not looking at the finite fields themselves, but the function fields in one variable over the finite fields. And within that function field, you could define things like exponential functions. And if you have that, you can expect there is also a thing as a logarithm. I've completely forgotten what the theory actually resulted into, but there may be tools there which can help you in your quest.
All right. Okay. Thanks.
So I'm not sure whether you see anything in this idea.
Yeah, I don't know, but I can just search for transcendent functions over finite.
The name of the colleague was Kobe Gijssel.
Maybe you can just write it in the chat.
Okay, I'll do so.
Well, Marius, you have, in fact, already taken away most of my questions by putting them as open problems. However, maybe you could explain a little bit more how this new notion of entropy does connect up with compression, data compression. You suggested that there was some connection. Is that right?
No. I mean, I don't know how it would connect. I mean, that's an open question. I would like to know what it's
also, yeah.
Yeah, no, I have no idea. Like, yeah, I guess the issue is that it's not continuous, that it's, it just has these discrete values. And
yeah.
So one has to define some kind of funny notion of compression.
Yeah.
but I think it should have interpretation like that. It's yeah. I think one just has to have the right definition.
Okay.
And there is, there's actually there's even more general papers. There's something called information cohomology, which is sort of an even more general way of thinking about these things. And I think that it's very interesting, and that it's sort of I don't know I don't necessarily know what it sort of means, but I think it's sort of, it just expands the notion of information in some novel ways, and I think it's always useful to have that.
I see. Yeah. Yeah. Thanks for a nice talk.
Other questions or suggestions?
Yeah, I have a question, Matt. So thanks for a very nice talk. I was curious whether you see any applications, or can explain a little bit about applications you have in mind of this. Is it, for instance, does this make it easier to somehow prepare these MUVs in certain scenarios, or is there something like that?
Yeah, actually, you mean the fact that we can map these line states to these map states? Like, what are the applications of this?
Yeah.
Yeah, actually, I don't know. So yeah, I'm just purely interested mathematically, but I think, yeah, I don't know what is the simplest way to prepare these states, but you could use this method, for example, to prepare them. I think, well, so Harry had some ideas about position-based cryptography that basically this unitary between these line states and map states. So I think what is interesting is the fact that, so I don't know, maybe you can go back, but so these, so basically these line states are, all of them are maximally entangled, because these lines, so unless you have a horizontal or vertical line, if the line, so let's say if you have just a line that y is equal to x, basically it just goes at 45 degrees, it literally corresponds to the standard maximally entangled state. And so all these lines are actually maximally entangled except the horizontal and vertical ones. And so what this circuit does, it basically maps this collection of different maximally entangled states, it maps them all to product states. And I think it's a really peculiar property that you can simultaneously disentangle all these states. And yeah, and actually, there was this workshop recently about these particle physics guys. They wanted to do some like a track tracing. And anyways, one way you could do this is to try to represent the track by a line, and then you could sort of map it with this unitary to these mob vectors, and then you can just measure in one of these mob bases, and you could try to kind of reconstruct your lines like this. But yeah, I don't know, like I think in some sense also the talk that I talked about Entropy mod P, I think it's really cool, but I don't know what it's useful for. And I just wanted to kind of bring it up so that people are aware that it exists, and maybe then somebody stumbles upon it or comes up with some way to apply it. But yeah, so I think what is the peculiar just here in this case is that you can simultaneously disentangle these states.